Okay. Chapter 18. Entropy, free energy, and then a little bit of equilibrium. So I am recording this. I'll post it to YouTube later today. I'll put a Canvas message out with the link to the video. Okay, so you can hear everything again. Bless you. Let's review just a little bit of some Chem 1 stuff. In Chem 1, for our book, it was chapter 5. I don't know what it was for you guys. You did a thermodynamics chapter, okay? You talked about heat and work, and you talked about enthalpy, and you talked about the first law of thermodynamics and the law of conservation of energy. So that should be ringing a bell to everybody, because those are Chem 1 topics. Now, do you remember the first law of thermodynamics? What does it say?
Yeah.
Come on, it's based on the law of conservation of energy. First law of thermodynamics.
He can't.
Exactly. Energy is not created nor destroyed, but it's only transferred. I'm not going to write that, okay? I'm just going to repeat it, but that's exactly right. Energy is neither created nor destroyed, but it's transferred from one form to another. And so when y'all remember doing that in physics or physical science? Remember the ball at the top of the hill has potential energy? Yeah? Mm-hmm. And it starts rolling down the hill and yada yada, it's converted to kinetic, et cetera, et cetera. Okay. So we're not talking about balls rolling down hills, right? We're talking about chemical reactions and sometimes physical processes as well. We also learned about system and surroundings. What's that? What's system? What's surroundings?
System is what's having stuff done to it, and surroundings is everything else.
Okay, very close. The system is the part of the universe that's of interest to us. Okay, system is the part of the universe that's of interest to us. Mm-hmm. And the surroundings, Matthew, you had that part. The surroundings is everything else. Now, as chemists, y'all, the part of the universe that's of interest to us is the chemical equation, right? It's the balanced equation you're looking at, or whatever, the process you're looking at. When we say the surroundings is everything else, we might be talking about, y'all, if it's aqueous, that means it's in water, right? Mm-hmm. That means water is the surroundings. And y'all, give me some feedback here, because when we did this in Chem 1, do y'all remember that the surroundings was like the beaker it's in, and you're the surroundings. If it felt hot to you, it's because it was giving you heat, etc. Is this ringing a bell? Mm-hmm. Okay, so talk to me about exothermic and endothermic. Well, hang on. Before we do exothermic and endothermic, now that we've got system and surroundings, and we've talked about the first law of thermodynamics, do you recall that we used positive and negative signs to denote which direction the energy was flowing? Mm-hmm. This is kind of, Matthew, what you were hitting on with it. Do you guys recall that since the system, what's the system? That's the part of the universe we're interested in. So if anything goes into the system, heat or work, that's positive to us. Okay? Because that's what we're interested in. If it's going into the system, y'all, where's it coming from? The surroundings, because of the first law of thermodynamics. So the surroundings is losing it negative, the system is absorbing it positive. Okay, if it goes into it. If the system is releasing any kind of energy, we denote that with a negative sign. Okay? And now if the system is releasing energy, where's the energy going to? The surroundings. First law of thermodynamics. So remember that when we're doing thermodynamics and we're doing positives and negatives, if we have a negative, it's not saying it's that much below zero, right? Like a negative 20 kilojoules means it's releasing 20 kilojoules. It doesn't mean it's 20 below zero. The positive and the negative sign on energy denotes direction. And so I just threw something else in there at you. Y'all remember joules and kilojoules for energy? That's our units. Okay, now let's review. Oh, I'm using my old app where I just scroll up. This one doesn't do that. That's why it's not scrolling. Sorry. Let's review now exothermic, endothermic, and enthalpy. Do y'all remember what the letter designation is for enthalpy? Capital H? Capital H stands for enthalpy. What is enthalpy? Come on.
Something to do with
Dig back
heat.
in. It is something to do with heat. Yeah, enthalpy is heat. Enthalpy is a measure of heat flow at constant pressure. So enthalpy is a measure of heat flow at constant pressure. Now that we've done enthalpy, yeah, enthalpy is a measure of heat flow at constant pressure. Now that we've done enthalpy, talk to me about exothermic and endothermic. Talk to me about exothermic.
It's the system releases heat.
System releases heat. How does that feel to you?
One.
Hot, warm. Why?
Because you're the one who's taking.
Because the surrounding is.
Because you're the one taking it in, because you're the surroundings. Yeah? What is the sign of the delta H when a reaction's exothermic?
H negative.
It's negative, right? You're exactly right. It's negative because that says the system's releasing the heat. So a negative delta H means exothermic. Positive delta H then means
Endothermic.
endothermic. How does an endothermic reaction feel to you?
Cold.
It feels cold. Why does it feel cold to you?
Because the system's absorbing heat.
The system is absorbing heat from you, and you are part of the surroundings. Okay, so is all of that like riding a bike? Y'all know what that means, right? It means you might not have done it in a while, but you can get right back on, and so we're good. Okay, now we're ready to get to chapter 18. We got to know all that stuff to get chapter 18. So, for starters, we're going to be looking at the idea of spontaneous and not spontaneous, or non-spontaneous, I guess we should say. So, the idea of spontaneous or non-spontaneous. Spontaneous means that a reaction will happen in one direction. Okay? That's what spontaneous means. That a reaction will happen in one direction. Oftentimes, well, in the context of thermodynamics, you will be asked, is this process spontaneous or is it not spontaneous? And let me tell y'all what I do to answer those questions in my head. I don't tell myself, is it spontaneous? I ask myself, will that happen? Okay? Because if it'll happen, that means it's spontaneous. For example, if I wrote this, H2O solid to H2O liquid. Now, that's not a chemical reaction. It's just a physical process. But what is that representing, y'all? What's going on?
It's melting.
It's melting. Ice melting. So the question would be, is that spontaneous? Well, really what you're asking is, will that happen? Well, you would all agree it depends on the temperature, right? Okay. If the temperature was like negative 30 degrees Celsius, will that happen? No. But in this room, will that happen? Yes. So what we say in terms of thermodynamics is we say like at negative 30, that's not spontaneous. Okay? At 10 degrees Celsius, it's spontaneous. So spontaneous and not spontaneous can depend on temperature. Now, what happens if it's at 0 degrees Celsius? What's the significance of 0 degrees Celsius for that process?
That's the freezing point of water.
That is the freezing point of water. So do you see at 0 degrees Celsius, y'all, that's your turning point for whether water is going to freeze and be in the solid form or melt and be in the liquid form. At 0 degrees Celsius, this process is at equilibrium. We talked about that briefly. Do y'all remember when I introduced the concept of equilibrium to y'all? And I talked about if you fill a glass with ice,
It's gonna like be cyclic, I'm trying to remember how you said it.
dynamic.
Yeah,
Dynamic is the word. You were going to say cycle. Yes, it's a
Yeah.
cycle. It's dynamic. When you put ice in a glass and you fill it with water, when you put that ice in the glass, it was individual cubes of ice. Okay? On the surface of that ice, you have ice melting and ice freezing. So some of the water you pour in freezes. That's why when you finish drinking all the water, the ice cubes are now fused together. Remember us talking about that? So when you have a process at equilibrium, like this process, 0 degrees Celsius, you do not call that spontaneous or not spontaneous, okay? Because equilibrium processes cannot be spontaneous. A key to an equilibrium process and defining it as spontaneous, y'all, it has one direction, okay? Spontaneous processes have one direction. In equilibrium, is it going one direction? No, man, it's going back and forth. So it's not spontaneous, okay? Now, let's first look at how do you know if something's spontaneous or not spontaneous? Well, some things like ice melting, y'all know that because that is a common process, and we know that in this room, ice would melt. We know that's spontaneous. That's what we call common sense. Yeah, just practical knowledge. But what if it's a process that you're not common sense about, right? That you're like, I don't know what's going on there. I don't know if it's spontaneous or not spontaneous. Then what you have to do is look at thermodynamic data. You look at enthalpy. We've talked about what enthalpy is, okay? The enthalpy, when you look at that, I know, y'all, hang on. Well, Faith, we get a kid. I'm so used to just being able to scroll up and, that's just what I'm doing. Sorry, I'm laughing at myself. Okay, enthalpy. A negative change in enthalpy. Y'all know what that triangle means, yes? Change in? Favors spontaneity. Favors. Does that say it is spontaneous? No. It says it favors it. Okay, this is all going to make sense once we get through. Okay, it does not guarantee it. So if a negative delta H favors spontaneity, then a positive delta H does not favor spontaneity. It doesn't guarantee it. It just looks like it's not going to be spontaneous or spontaneous. Well, this process. Do y'all know what's going to happen here? That's methane and oxygen. Do y'all know what the products are? What kind of reaction am I writing?
Is it only CH4O2?
It's not. Carbon dioxide and water. How'd you know that? It's combustion. I didn't tell you combustion. I was trying to get you to recognize it. So, yeah, that's a combustion process. Balance. There we go. Okay. Number one, do y'all know if the delta H for this process is positive or negative? I think you know the answer to that. It is negative. How do you know the delta H for that is negative?
Because it's releasing heat.
It's releasing heat. Here I am coming at you with another question. How do you know it's releasing heat?
that's cool.
Because it's combustion. Yes? Combustion processes release heat. So if you see a combustion process, y'all, you know the enthalpy change is negative. Now, I'm not going to write the number because I don't remember what it is. It's like, I don't know, I could make something up. But I won't. It's like 600 and something kilojoules. I don't know. Okay, it releases heat. So, based on the sign of the delta H, we would say, oh, that favors spontaneity. Okay? And y'all, we know that reaction will happen. Methane will burn. If you light it on fire, it's going to burn. Okay, but that's what the negative delta H says. Okay, we were just talking about this process. At 25 degrees Celsius, is this process spontaneous? We know it is. We know that ice melts at 25 degrees Celsius. 25 degrees Celsius is in this room. But we also know that the delta H for this process is, don't we know it's positive? Don't we know that ice melting is endothermic?
Mm-hmm.
How do we know that?
Because it feels cold to us.
Because it feels cold to us. We hold it in our hand, it feels cold. We know it's endothermic. So right there, we have a process that even though the delta H is positive, y'all, the rule says that if the delta H is positive, it does not favor spontaneity. However, we know that is a spontaneous process. Are you with me? That what the sign of the delta H says contradicts what we know about the process. But that's okay. Why does it contradict it? Because there's more thermodynamic data to consider besides just enthalpy. Okay? There's something else to consider. What is that? Well, the something else to consider is called entropy. E-N-T-R-O-P-Y, entropy. The symbol for entropy is a capital S. Entropy is defined as a measure of disorder, a measure of how spread out or how dispersed is a system's energy. Okay? Early on, I'm going to come back to this slide, y'all, but I'm about to flip. We've talked about enthalpy. And enthalpy units, guys, if you'll remember, those are usually kilojoules per mole. That's enthalpy. Enthalpy is usually a whole lot of energy, so we do kilojoules instead of joules. Now, to contrast that, entropy is not a lot, so we don't use kilojoules, we use joules. So typically your units for entropy are joules per mole times Kelvin. Okay, joules per mole times Kelvin. Now, when you're taking a test, when you're doing Connect or whatever, you don't have to remember the units. The units are going to be there. But y'all, on down the line, like by Wednesday, we're going to be putting together enthalpy and entropy, and we're going to add them together. But if enthalpy is coming at you in kilojoules and entropy is coming at you in joules, can you just add them together? No, you've got to make sure your units match. So I'm telling you now to watch for that. Okay, that you've got to just make sure your units are jiving. You'll know what they are, but I'm telling you the entropy is going to be in joules. Now, all that, let's get back to what is entropy. A positive entropy favors spontaneity. A negative entropy, then, favors I know I'm changing the form of the word, and that's annoying, but it favors non-spontaneous or non-spontaneity. Non-spontaneity sounds funny. do y'all catch that the signs I'm giving you here are the opposite signs of what enthalpy is? Okay, so, I mean, let's realize that. The signs here are opposite of what enthalpy is. What is entropy? Well, guys, if I have, this is a big old container, okay? And this is a partition in between the two sides. And this whole container is sealed off, okay? Y'all, if I have this side of the container filled with a gas, tell me what's going to happen when I lift up this partition.
Gas getting out there.
Gas is going to spread out. Look at your definition of entropy. A measure of how dispersed it is. Do y'all see that right now, maybe I've got a low entropy? Do you see that when I lift that partition and it spreads out, it's going to be higher entropy? It's going to be more dispersed, okay? We would define this as a very simple explanation, but we would define that as spontaneous. Nobody in here thinks that when I lift up that partition that all the gas is going to stay on this side. It's not going to happen. We know that when I lift that partition up, the gas is going to spread out. Plain and simple. That is going to increase its entropy when it spreads out more. We can see that. Do you see that what you're doing is you're qualitatively telling me? You have no idea what the number's going to do from here to when I lift the partition. That was me. But you do know that it's going to go up. Do you see? You don't know if it's going to go up by 5 or 10 or 100 or 10,000, but you know entropy is going to increase when I raise that partition. That's qualitative. Now, is this process reversible? Well, when you consider whether a process is reversible or not, guys, if I lift the partition, the gas spreads out. Reversible means I have to do exactly opposite of what I did to make it go forward. So reversible means that I have to drop the partition down. If I drop the partition down, is it going to go back to looking like it does right now? No. What's going to happen when I drop the partition down? I'm going to have gas trapped on both sides, right? So do you see that this process, it's not reversible in the parameters that we're talking about? Now, it is reversible because if I lifted this partition up, the gas spread out. I could have some kind of piston over here, and I could shove all the gas back over, shut the partition, remove the piston, and I'd be back to this state, right? But getting it back to this state, did I take the same path as I did to get it spread out? No. So that's why we would still call it non-reversible, because you have to take the same path forwards and backwards. Okay. Let's look at some qualitative predictions of entropy. Qualitative. One thing I can look when I'm deciding is entropy going up or going down, I can look at the states, okay? Solid to liquid to gas. Think about this, y'all, on a molecular level. Do y'all know that solids have definite order? Yes? Liquids, aren't they more random in there? Gases, they're all spread out, much more dispersed. What I'm trying to tell y'all is that if a process is going from a solid to a liquid, or from a liquid to a gas, or from a solid to gas, this flow here, solid to liquid to gas, does it make sense to y'all that it's increasing entropy?
Yes.
Okay, increasing entropy. It's getting more random as you go from a solid to a liquid to a gas. So if that is increasing entropy, then if I'm going from a gas to a solid, obviously that's getting more ordered, yes? That's a decrease in entropy. And that's one thing we can look at. Another thing we can look at for like molecules, we could compare a molar mass. For like molecules, you could compare a molar mass. So, when we're looking at the first one, solid to a liquid or a gas, we're looking at how the molecules are with respect to each other. But let's consider the noble gases. Those are like molecules, right? Because they're all monoatomic. When we look at the periodic table and we look at the noble gases, clearly as we go from helium, neon, argon, clearly the molar mass is getting bigger. Yes? So if the molar mass is getting bigger, y'all, doesn't that mean there's more protons and neutrons in the nucleus? Yeah. Doesn't that mean that the molecule is getting more spread out? Remember learning that in Chem 1, that radius increases as you go down because you got more electrons? So more electrons, isn't that going to be more dispersed? So if I asked you helium or krypton, which one would have greater entropy, what would you tell me? And you got to support your answer.
Krypton.
Krypton. Why?
Because there's more molecules to spread out.
There's more subatomic particles to spread out. Electrons are more dispersed. And really what I'm doing to get a quick answer on that, y'all, is you're just looking at the molar mass, okay? But it's not all about the molar mass. The why is in because the subatomic particles are spread out, okay? Do you see, likewise, I could compare methane, CH4, to ethane, C2H6? CH4 versus C2H6, which one's going to have more entropy?
C2H6.
C2H6, one with the higher molar mass, because it's made up of more atoms and more electrons. So it's going to be more random.
So you'll mark off if you just say, the molar mass is bigger than this molar mass?
When you are explaining why is the entropy greater, it's a quick look to consider just molar mass, but that's not the why. The why is because of the greater number of subatomic particles. Okay? Molar mass is getting there. It's getting to an answer. Okay? But what I also want you to say, to understand on that, because, to hit on what you're asking, I can't ask you helium versus hydrogen. Why can I not ask you that?
Because they're not
They're not
the
alike.
same.
Helium is a monoatomic thing. Hydrogen is H2. It's a hydrogen and a hydrogen. I can't ask you to compare that. Okay? Because you know what I would do if you asked me? I'd go look up the entropies for them. Okay? So it's always going to be in like molecules. This is a table in your book, and it goes over some of what we've just said, okay? So these are entropies. I'll see them. There's your units, right? They're there for you. You just got to recognize that it's joules. So if I had covered this up, I know, let me show it to you. If I covered that up and said, oh, here's H2O liquid and H2O gas, which one's going to have higher entropy?
The gas.
The gas. Why?
Because they're more dispersed.
They're more spread out. Look, it's what you predicted. Here's a quantitative value, but qualitatively, y'all knew what was going on there. Look here. This is doing it again, right? Sodium solid versus sodium liquid.
Liquid.
Makes sense. Here, helium and neon. They're both gases, but we recognize what?
Neon will be larger.
Right, that neon will be more because it's smaller mass, because it's more spread out. Okay? That's just kind of a table summarizing some of the different stuff that we've looked at and qualitatively predicting it individually. Now, let me write some chemical equations, and you guys tell me whether entropy is increasing, means getting more random, or decreasing means getting more ordered. Are we solid on that? On what it means to be increasing and decreasing? Okay. So this one. calcium carbonate makes calcium oxide and CO2 gas. What we're going to do, and what that says up there, we are going to predict the sign. I didn't write all that. We're going to predict positive and negative. What is the delta S of the system? What is the entropy change of the system? Remind me, we're chemists. What is the system? It is the balanced chemical equation. That is our system. Okay? So what I want y'all to tell me, if I start with some solid calcium carbonate, and what makes this happen is heat. It'll break down, y'all, into calcium oxide and carbon dioxide gas. Do you think that that's getting more random or less random?
More?
I think it's more random. Tell me why y'all went with more. You're exactly right.
Because the gas.
The gas.
You are producing a gas. I predict that this is positive. Okay? And you're right. I mean, it is. We'll calculate it in a minute. Okay, what about this one? Nitrogen gas and hydrogen gas makes ammonia gas.
I still think it would be plus, because that's bigger than what you had in the beginning.
Okay. You've got some molecules of nitrogen in too. You got 3 times as many hydrogens, H2. Clearly, this stuff's going to rearrange. The nitrogens and hydrogens are going to rearrange. Because now, instead of nitrogen bonded to nitrogen and hydrogen bonded to hydrogen, the nitrogen's going to bond to 3 hydrogens, and there's only going to be 2 moles of those. Okay? Okay? I'm hearing positive and I'm hearing negative. What you need to do when they're all gases, or whether it's all aqueous or whether it's all liquid, solids, it's not going to be all solids, but if it's all gases, look at how many moles of reactants do you have? 4. That organizes into only 2 moles of product. Do y'all see? I kind of gave it away because it organizes.
So
It's
it'd
going to be a negative because it's going to organize into only 2 moles of gaseous product. Then the next one, hydrogen gas and chlorine gas, makes 2 moles of hydrogen chloride gas. Well, Miss Tara, they're all gases, so I can't look at that. And then when I look at how much, well, I start with 2 moles and I end with 2 moles, so I can't look at that. So it's kind of a trick question, but what I want y'all to realize, that's hard to predict. So if we can't predict it, maybe we could calculate it.
Is there like like how there was on this where we had a equilibrium, so we couldn't, is that a thing with entropy?
Entropy.
You know what I'm trying to say?
Mm-hmm. I don't know.
Okay.
It's not going to be 0. I don't know how to answer that.
That's okay.
Okay.
If you don't know, I don't have to worry about
Okay. But I feel like that's something I want to think about and figure out. She asked about entropy and equilibrium. How do you predict that when it's equilibrium? And so I'm only going to ask you to predict ones that are going one direction. I don't know because I'm not smart enough in terms of thermodynamic stuff to know. But if somebody explain it to me, y'all have been there, right? Somebody explains it to you and you go, oh yeah, that makes sense. Why didn't I think of that? That's probably what I would say. So that makes perfect sense. Okay, let's look at how to predict them. This is the formula for predicting entropy change of a system. Which I really sincerely hope it looks familiar.
Mhm.
Okay, it looks familiar to Emma. Does it look familiar to everybody? Good. Hannah says it looks familiar. Guys, you used a formula like that in Chem 1. Do you remember that? That's why I'm asking you, does it look familiar? In Chem 1, you did this formula. The delta H for a reaction is equal to the sum of the enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants. So, I just said it when I was writing it. Those funny looking E's, mathematically those mean sum of, S-U-M, sum of. What are the N and the M? What do those stand for? Not here. Usually N is moles, but not here. Means the coefficients. He does. The N and the M are the coefficients, and then it's products minus reactants. Okay? So, look, here's what I'm wanting to do. We predicted for that first one that the sign of delta S was positive. We are now going to calculate it. We're going to calculate it using this formula. So how we use that formula is we take our balanced equation, we go to a table of data. Dariana?
To predict the positive and negative system, can we use the last one that we were trying to follow, the question mark,
Instead of the first one, I'm going to do both of them.
Okay.
I'm going to do the first one, and then I was going to do the last one. I'm going to do the first one because y'all know it's going to be positive, right? We predicted it, and I wouldn't lead you astray. It's going to be positive, okay? But then I am going to do the last one and talk about what that means. So I'm going to do both. Now, hang on. I'm going to take a picture of this for y'all. Where do we get the standard enthalpies of formation or the entropies from?
Hopefully a table.
There's a table, and I'm going to take a really I know you can't read it, okay? But that's okay, because on the test you would be able to see it clearer. But what happens, y'all, is it's really alphabetical. This is Appendix 2 in your book. And when you have these on Connect is probably not going to have you go to Appendix 2. Connect's probably going to have them listed for you with the problem, okay? But when you start to work the end of chapter problems, you're going to have to go to Appendix 2 in the book, because the end of chapter problems aren't going to have it for you. So what we're looking at, y'all, we need to look up calcium carbonate, and it's at the bottom. I'll tell you what it is. I'll draw an arrow by it. That says calcium carbonate solid. Now, what I want y'all to look at, let's see. Oh, that doesn't get, I can't get it bigger for y'all. Y'all, this says H. This is enthalpy, okay? This says G. That's known as your Gibbs free energy. We're going to do that in this chapter, but we're not there yet, okay? This last number is your S. It also has, and I don't know, Kaylee, you're probably the furthest one away, but it has the units. These units are kilojoules per mole. These units are kilojoules per mole. This is entropy, y'all. It's joules per Kelvin mole. So it has the units, but this is just me reminding y'all again, they're not all in the same kind of joules. Okay, so we're gonna look up the S for calcium carbonate, and it happens to be 92.9. 92.9. I'm not gonna write units on this because I end up with a lot of stuff, but I know it's joules per Kelvin mole, and y'all do too because you just saw them. Okay, then I'm gonna look up calcium oxide, which is right there. Y'all, it's 39.8. And then I'm going to look up carbon dioxide gas, which is right there. And it's 213.6. Okay, so the first thing I do with this formula is I am looking up the S's from the table. The second thing I do, and this is also why we're going to do another one, is I multiply by the coefficients. I'm going to write that on this one. Y'all, what are the coefficients on this one?
One.
They're all 1, but I'm going to write that. You wouldn't have to write this, but I'm going to put that on there because it's kind of a reminder when I'm teaching it that, hey, we got to multiply it by the coefficients. So I have all the same numbers, right?
Mm-hmm.
Then what do? What does that little funny looking E mean?
Sum of.
Sum of. What do I sum up? Do y'all see I sum up just the products? And then do you see that I sum up just the reactants?
Mm-hmm.
Just the products is 253.4. Just the reactants is 92.9. Then I'm ready to calculate the delta S of the system. Products, 253.4 joules per Kelvin mole, minus reactants, 92.9 joules per Kelvin mole, the delta S of this system is 160.5 joules per Kelvin times mole. What did we predict? We predicted it would be positive, didn't we?
Mm-hmm.
Y'all, it is positive. This is your only one to have calculated so far in your life, and so you wouldn't know this. But, guys, a positive 160.5, that's a big entropy change. Okay, so that one was easy to predict. It was positive delta S. Okay, now, let's do the one that we couldn't predict, the hydrogen and the chlorine one. So, hydrogen gas plus chlorine gas yields 2 hydrogen chloride gases. And before I go on and I'm doing that, let me remind y'all of something else you learned in Chem 1, okay? It was here, it's where you learned it. In Chem 1, all we ever looked at was this first column of stuff, these enthalpies. Y'all, if you look, can y'all see, even if you're in the back, that one's a 0? That's graphite, that's carbon. Elemental carbon is 0. There's another 0. That's calcium, solid. Elemental calcium is 0. I do have another 0 at the bottom that I got in the picture. That's cadmium. Do y'all remember from Chem 1 that if you have an element, its enthalpy is going to be 0? Okay, so you don't have to know that. You don't have to be given that in your table. But realize that carbon elemental is just carbon, calcium is just Ca, sodium would be Na. But elemental oxygen is going to be O2. That's the one that's going to be 0. Okay? So those are 0. Look at your entropies. The elements are not 0 on entropies. Okay? That only applies to enthalpies, not on entropies. You're not going to have a 0 on your entropy. Now, what I'm going to do is I'm going to look these up. Instead of taking a picture and circling them, I'm just going to look them up and tell y'all what they are. And y'all are going to do that fun little equation. All right, hydrogen gas, its entropy is 131.0 joules per Kelvin mole. Chlorine is 223.0. And then hydrogen chloride gas, let's start with the chlorine, is 187. Do y'all know what I need you to do with those numbers? I need you to do that delta S is equal to the sum of the N and the M and the da-da-da-da-da. Okay, so y'all work that one. Y'all getting 20? Okay. We now know that the sign of it's positive. Okay? It was hard to predict, y'all. 20 that's a small change in entropy. But do you see that the first one was easier to predict because it was 160. That was big. 20 is really small. When the delta S is hovering around 0, that's a small change. That's why it was hard for us to predict. But now we know that it's 20. Okay, so don't forget to multiply by the coefficient. Y'all caught that in this one. All right. Now, let's talk about the universe. Mwah! Okay. Tell me again, what's the first law of thermodynamics?
And it can't be destroyed or created or transferred.
Energy is not created nor destroyed, it's only transferred from one form to another. Okay. First law of thermodynamics applies to enthalpy. It says that the delta H of the system is equal to the delta H of the surroundings, but opposite sign.
What are we talking about?
We're talking about, you want me to do it again with the whole laugh and everything?
No. Like, what does that apply to?
Enthalpy, first law of thermodynamics.
Okay.
We're going to the universe. That's what we're going to. Okay? Y'all, if a system absorbs 20 kilojoules of energy, then the surroundings had to release it. That's what this is saying. So if the system absorbs 20, that's positive 20. That means the surroundings was negative 20. Okay? So that means if the system released 100 kilojoules of energy, that's negative on the system. That means it's a positive 100 on the surroundings. Yes? Okay. The delta H of the universe is talking about the delta H of the system plus the delta H of the surroundings. Well, guys, the first law of thermodynamics says that the system and the surroundings, they always have the same number, just opposite sign. So then doesn't that mean that the delta H of the universe, yes, it's 0. Very good. Okay, now here is the catch. That, you cannot substitute an S in for that. Entropy does not follow that. Now, this is fun. Ice melting. And y'all, let's just go at room temperature, okay? 25 degrees Celsius. I want us to predict the delta S of the system. I want us to predict positive or negative. And I want us to predict the delta S of the surrounding, positive or negative. Okay? System's easy because we've already talked a lot about that. The system's what we're looking at. Y'all, when ice melts, solid to liquid, clearly that system is a positive delta S. Agree with me? Okay. Now let's think through it. Guys, when ice melts, if I'm holding it in my hand, well, I'm part of the surroundings. I'm going to get colder. The air's going to get colder. Whatever it's in is going to get colder. What happens to the movement of molecules as they get colder? They slow down. Does it make sense to you then that the delta S of the surroundings would be, it's negative? If they're getting colder, aren't they getting a little bit more organized? That's exactly what's happening, okay? Now, next example. Yeah. What if I have water that's boiling, 100 degrees Celsius, and I'm going to water that's 25 degrees Celsius?
System be negative
The system would be negative. Why?
because the system is releasing heat.
Because it's releasing
Well-
heat, but the molecules are slowing down as they cool off. So they're getting a little bit more ordered. 100 degrees Celsius water, they're moving faster than at 25 degrees Celsius water. Okay? What's happening to the surroundings?
The heat that it's releasing is, so it would be positive.
Yes, the heat that it's releasing is going to make that positive. Very good. Okay? Now, the other one we want to look at, and these are the ones your book goes through, y'all. This is page 845 in your book, and you can read their explanation if you want to. I mean, obviously you want to read it slow, right? But it goes along with all these filling in words that I'm doing. Oops, I think that's a liquid, yes. Makes H2O liquid and oxygen gas. Okay, so I got two H2O2 liquids, which is hydrogen peroxide, and it's breaking down to make water and oxygen gas. What do y'all think the sign is for the system?
It's gotta be plus, right? Because it's making a gas.
Yep, got to be plus because I'm making a gas. Yes? Now, you don't know about surroundings because I've got to give you a little more information. Y'all, I'm going to tell y'all that this process is exothermic. What does that mean? It's releasing heat. That tells us what the surroundings are. If it's releasing heat to the surroundings, then the surroundings are warming up. What does that mean the sign of the S is?
Plus.
It's plus. Do you see, based on our explanation, that the delta S of the surroundings is going to be related to the delta H of the reaction? If it's exothermic, that means delta H is negative. That means this is positive. Okay? If it's releasing heat to the surroundings, hot water, cooling off, that means it's releasing heat, delta H is negative, that means S is positive. If ice is melting, we know the delta H is positive, that means the delta S of the surroundings is negative.
So really, we should be paying attention to H and
The,
surroundings.
yes, the sign of the delta H tells us what this is. It's just going to be the opposite sign. Okay? There's a formula that the delta S of the surroundings is equal to the negative delta H of the system divided by the temperature. Okay. In these three examples, y'all, look at our signs for system and surroundings. The system's positive, the surroundings is negative in one. The next one, you've got the opposite thing happening where you got a negative and a positive. And the last one, you have two positives. Y'all, I can never, ever give you an example where both of them are negative because that can't happen. That is the second law of thermodynamics. For a process to be spontaneous as written, the delta S of the universe must be positive. For a process to be spontaneous as written, the delta S of the universe must be positive. I'm going to. Okay, I'm jumping back to the previous slide. How do we calculate the delta S of the universe, y'all? It's the system plus the surroundings. And I told y'all going into this that these don't have to be the same number. Do you see that for this first equation, in order for the delta S of the universe to be positive, this one has to be a bigger positive than this one is negative? Okay, do you see that in this one? In order for the delta S of the universe to be positive, you have a bigger positive number here than you do a negative here, et cetera, et cetera. Do you see why you can't have two negatives? Because then the delta S of the universe would be negative. And you can't have a spontaneous process that has the delta S of the universe with a negative number.